let's look at how to solve the wave equation in 1D while looking at a vibrating string. So we take an initial shape of the string. We can imagine how we're just pinching the string up and then let it go, and we want to see how this string evolves over time, how it vibrates while being blocked at 0 and L. So we have that the second derivative with respect to time of y being the shape of the string at time t and position x, is equal to c squared second derivative of y with respect to x. We're solving for x between 0 and capital L and any t positive. We are fixing the boundary conditions. We want y at 0 for any time being equal to 0, and y at capital L for any time being equal to 0. And we're going to give you initial conditions. I'm going to say that y at time 0 is equal to f of x. And I'm going to give a second initial condition. The derivative with respect to time of y at x at time 0 is equal to g of x. Why do I need two initial conditions? Up to now, the Laplace equation had no initial condition. The heat equation had one initial condition. And now the wave equation has two initial conditions. The reason is that the initial conditions depend on the order of the highest derivative with respect to time. In the Laplace equation, there is no derivative with respect to time. Time doesn't enter in the Laplace equation at all. So we don't need initial conditions. On the other hand, the heat equation has one derivative with respect to time. So we need one initial condition. Now we have a second order derivative with respect to time, so we need two initial conditions. It works in a very similar way as the ODE systems we have worked with. The higher the order of the highest derivative is, the more initial conditions we need. So if you want to look at it in a different way, what we want to solve this equation on is an infinite strip in which we have x on the horizontal axis fixed between 0 and L, and t being any positive value. And we are fixing at the bottom of this infinite strip, we want y equal to f of x and y dot equal g of x. At the boundary of this strip, we are setting y equal to 0, and in the center of it, we want the Laplace equation to be satisfied. As we have done many times, we will approach this in a separation of variable kind of fashion. So we're going to say that y, function of x and t, is the product of x function of x and t function of t. If we apply the Laplace equation, what we retrieve is that c squared x second t is equal to t second x. As I've done multiple times, here the primes indicate different derivatives, the derivatives with respect to different variables depending on where they're placed. So t second is the second derivative with respect to time, while x second is the second derivative with respect to space. We can now shift things around. We're going to choose to have a Sturm-Liouville problem with respect to x, because if you notice in the x direction, we have trivial boundary conditions, so that's the one we want to have. And we're going to solve x second divided by x equals t second divided by c squared t. As many times we have seen, this is an equality between a function in x and a function in t, so there needs to be constant all the time. So we are setting this equal to k squared, and we can choose the sign in front of the k squared. We want a Sturm-Liouville problem with respect to x, so we're choosing a minus sign in here. So we write the Sturm-Liouville problem with respect to x. This is a Sturm-Liouville problem we should know pretty well by now. So we have x second plus k squared x equal to 0, and trivial boundary conditions on the two sides. X at 0 is equal to 0, and x at L is equal to 0. And we know that the eigenvalues in this case are kn being n pi divided by L. Actually, the eigenvalue is the square of this, for n going from 1, 2, and so forth. And the eigenfunctions are sine of kn x. Then we go to the time part of the equation. So we have t second divided by c squared t equals minus kn squared. By now, well, we know that c squared is positive. We know that kn is real and positive itself, so kn squared is definitely positive. So we know that Tn is a sum of sines and cosines. And here is where you notice that we need initial conditions for t and t prime because we have a second order equation on t. So we're going to be composing the solution as we have done multiple times. We're going to have an infinite sum in which we have all the sine kn's that come from the Sturm-Liouville problem and the block that comes from the solution of t. So an sine ckn t plus bn cosine ckn t. We still don't know an nor bn, but we can use the initial conditions to fix both of them. Because if we set yx at t equal to 0, then we know that we have an infinite sum of only bn times sine knx equal to f of x. This f of x is the initial condition that we have set, and sine knx is the eigenfunction of the Sturm-Liouville problem we have set. So from the Sturm-Liouville theory, we know that the coefficients of this infinite sum can be found by setting bn equal to the inner product between f and sine knx divided the inner product of sine knx by itself. What inner product are we using? Well, the one associated to the Sturm-Liouville problem that we had at the beginning, that is the standard inner product between 0 and L. So the integral between 0 and L of f of x sine knx dx divided the integral between 0 and L of sine knx all squared dx. So now we have a specific formula for bn. Let's look at the formula for an. So the derivative with respect to time of y computed at x and time equal to 0, we drop the term depending on an, so we only have an infinite sum of an ckn times sine knx equal to g of x. So on these two sides we have two functions of x, and on the left side we have sine knx, that is the eigenfunction, sorry for the typo, the eigenfunction of a Sturm-Liouville problem that we have solved. So we know that an ckn can be computed from the Sturm-Liouville theory. On top of that, we know c, it comes from the problem, and we know kn. So we have a formula for an that is based on the Sturm-Liouville theory that says that this formula is inner product between g and sine knx divided inner product of sine knx times itself. And if we want to find an, then we also have to divide all of this by c and kn. If we look at the final solution, if we place all of this together, I would like to point out some properties of this solution. We have y being an infinite sum of, in x, something that is a sine, and in t, something that is a combination of sine and cosine. This solution oscillates both in space and in time, but it does not dissipate. There is no term that is decreasing over time. There are only terms that keep oscillating with the same width all the time and all the space. While the process of solving this can be very similar to how we solve the heat equation, this solution does not dissipate. The wave equation solutions do not decay to a steady state. While for the heat equation, we would divide the problem into solving the steady state, that is a Laplace equation, and the transit state. This doesn't work for the wave equation. We have oscillations that don't dampen. We are not tending to a steady state. This is obviously unphysical. If you pluck a string, sooner or later it's going to stop oscillating, but those are terms of dampening that we haven't introduced in the wave equation itself. When we go back to the equation that we have solved, we notice that what we have used in order to build up the Sturm-Liouville system is that on the both sides of our interval, so on the two boundary conditions, are trivial and Dirichlet boundary conditions. We need that for the Sturm-Liouville system, but you notice that if we were to replace either or both of them by a y prime equal to 0, that is a Neumann boundary condition, it will work the same way when we are up to the Sturm-Liouville problem. If we have instead a combination of y and y prime, that is a Robin boundary condition, we will still be able to write the Sturm-Liouville system and solve it. It just would be harder. Looking at the solution again, we notice that the frequency of oscillations, so if we're focusing at one value of n, so we're just looking at, for example, n equal to 1 or n equal to 2, well, sine kn x, for example, n equal to 1, is just 1/2 of a sine. And we are associating that with something that oscillates in time with a given frequency. So sine cknt. This frequency is the frequency associated with the standing wave with a given n. And you can think of n equal to 1 as the wave that has just one tip, one half of a wave, really. N equal to 2 is a full sine. N equal to 3 has 3 wiggles, and so forth. So the higher n, the more wiggles you have in your sine kn x, and the part that depends on t just tells you how fast it's oscillating over that.